Okay, thank you. All right, hello, I'm Jacob, and I'm going to present Pantograph, which is a fluid and typed structure editor. This is joint work with Henry Blanchette and my advisor, Leo. And in a minute, I'll get to what I mean by fluid and typed. But first, let me talk about structure editors. So here's you programming in a text editor. There's the programmer on the left. You're writing a text file that says 4 + 5. I guess it's a very ambitious piece of software that you're working on. And in a text editor, that text file is parsed into a syntax tree. And then that syntax tree is typed to produce an annotated typing derivation. So you're familiar with this pipeline in a text editor. But in a structure editor, on the other hand, we have no need for a text file. There's no text file. And instead, the programmer directly writes the syntax tree. Now, in many structure editors, the programmer is writing an untyped syntax tree, which is still then type checked to produce a typing derivation. But in some structure editors, like Pantograph, the programmer is directly writing a typing derivation. So in Pantograph, there's no intermediate representations for the program at all. There's no text. There's not even an untyped syntax tree. So what does this look like? What does it look like to directly edit a typing derivation? Well, let me show you a basic structure editing setup. So here's a blank program in Pantograph. Here we have a hole of an unknown type. And what you can do with the hole is you can fill it in with an expression. So for example, I could put a plus expression into the hole. And now I'm left with two new expressions of the type int, which are the children of the plus expression. And for example, now I could fill these numbers 4 and 5 into the holes. And another thing I can do is I can wrap an expression around an existing one. So for example, I could put this if expression around the 4 + 5. And one final thing you can do in this basic structure editing setup is you can cut and paste entire terms. So for example, I could move the 4 + 5 to the other branch of the if. So what I've just shown you is a very traditional plan for a structure editor. To recap, you have these typed holes that represent unfinished parts of the program. You can fill expressions of the correct type into the holes, and then you can move entire terms around. And this is nothing new. This idea has been around for decades in various forms. There are some basic advantages of this approach. We'll get to some more interesting advantages later, but there's no compile time errors, right? There's no parser, so you can't have a parse error, and there's no type checker, so you can't have a type checking error, right? The programs are just directly correct by construction. But there's a well-known flaw with this basic structure editing setup, which is how do we edit existing code, right? Filling in typed holes is all well and good as long as you never make a mistake, but what if you have to actually go back and edit something? So for a minute, I'm going to be using this example. We have these two little function definitions, double and square of the type int to int, and then the call at the bottom, double the square root of 10. So for example, suppose that I want to swap the order of these two definitions, or maybe I want to swap the order of these two function calls. Well, to do this in this basic structure editing setup, first of all, I need a hole to do anything. And then it's actually going to take 4 cut and paste operations to do this. So there's the first one, there's the second one, there's the third one, and here's the fourth one. So it's a very clunky interface to do a basic thing like this. And even worse, what if I want to make an edit that actually changes the types of something in the program? So for example, maybe I want to add an argument to this double function. Well, if I'm allowed to add this lambda here, then the program is no longer well typed. So this seems to conflict with the idea that we're editing a typing derivation directly. So the challenge that we set for ourselves for this project is, can we make a structure editor in which the programmer is directly editing a typing derivation, but yet we can still freely or fluidly edit the program, edit existing code? And there's other approaches you could take, like Hazel adds another kind of intermediate representation, but this is the idea that we're pursuing. So to solve this problem, Pantograph introduces 2 ideas. The first is tree selection, which will help us to rearrange things in our program more easily. And the second is an automatic type refactoring system in which each edit will have a typed meaning. So here's this double square thing again. And in a tree editor, the cursor goes on expressions. So we could put the cursor on these let expressions or on these function calls. And we've seen how it's very difficult to rearrange things by just moving entire expressions. But by contrast, in a text editor, it's very easy to rearrange things. So what does a text editor have that a tree editor doesn't? Well, in a text editor, we have a cursor, which goes in between characters in the string. And we've just seen that in a tree editor, the cursor goes on expressions or on nodes of the tree. But in a text editor, there's a second thing called a selection, which goes in between 2 possible cursor positions. So the idea that we had is, let's extend this by analogy to a tree editor. And so that a cursor in a tree, or a selection in a tree editor should go between 2 possible cursor positions. In other words, it goes between 2 expressions. And specifically, the tree selection is the area inside of one expression and outside of another expression, known in PL as a one-hole context. So let's look at how we can use these tree selections to actually rearrange things in the program. So for example, I can make this selection by clicking and dragging from one expression to another. There I've selected the area inside of the double function call, but outside of the square function call. I can then cut that, which puts it in my clipboard and removes it from the program. And then I can place my cursor on the 10 and paste it, and now I've rearranged those two function calls. Similarly, I can use the same principle to rearrange these two let definitions. So I've made this selection, the area inside of the first let expression, but outside of the second one. I can cut that, and then I can paste it on this expression at the bottom, and now I've rearranged my function definitions. So it turns out that this concept of tree selection corresponds to quite a lot of common program edits. So let me show you some of them. So we've just seen the one about reordering function calls, and this is that again, but in this case, the function call that we're moving has two arguments, and the inside of the selections in the middle. So this is just to show that there are tree selections that don't correspond to text selections, right? This takes 2 steps in a text editor. We can also use a tree selection to rearrange function arguments. So in this case, these are curried applications. The tree selections actually work nicely with curried applications. You could also use a tree selection to reassociate binary operators. This is actually the same thing again as just reordering the function calls, right? So in a text editor, this would be different, but on the tree structure, this is the same operation. And one last one, on cons lists, these tree selections end up corresponding to just selecting a sublist, right? So they correspond to just usual list selections, and then we can use the tree selections to reorder things in the list. So I've shown how we can use these tree selections to more easily rearrange expressions in the program. But remember, there was this other problem of what if we want to make an edit that actually changes the types of things? So here we wanted to add an argument to this double function. And let's just go ahead and see what happens when we actually do that in Pantograph. So I can place my cursor on this expression, and I can add the lambda. And what's happened is that Pantograph has automatically changed some stuff in the program in response. So I just added the lambda in green. Pantograph automatically added this argument to the annotation at the top, and it also automatically added the whole argument at the call site at the bottom. So this might be familiar if you've ever used like an IDE or a language server where there's some feature where you like right-click on a function, add argument. It might do something like this. But in Pantograph, actually every single edit is a typed refactoring. So let me show how this works on a higher order function. So for example, here's a map function. It inputs this parameter f of the type bool to bool, and then it's taking a list of bools, outputting a list of bools, and at the bottom, I'm mapping the function not over this list. So suppose that I want to add a higher order parameter to f. Maybe I'm turning this into map with index or something. So let's do that in Pantograph. So I can add this argument here in the annotation. And again, Pantograph automatically added some stuff. It changed the annotation at the top, and it added the argument to f. But here, the not at the bottom, which used to be of the correct type bool to bool, it's actually wrapped a lambda around the not to fix the type of that. So let's take a look at how this typed refactoring system actually works. And to do that, I'm going to use essentially the simplest possible example, which is this very small program, lambda x.x applied to 10. The programmer here is inserting a lambda around the 10, and then Pantograph will respond by adding an argument at the call to the x. So to represent the way that the types of things change, Pantograph uses what we call diffs, like diffs from version control. So that this 10 expression, it used to have the type int, and now lambda wide at 10 has the type int to int. So the diff plus int to int expresses that we've changed the type by adding this int arrow to it. And what Pantograph does is it will propagate these diffs through the program step by step to make the edit. So this is the starting point, is that we're at this expression, we've just changed the red expression, and we know that we need to change it according to this diff plus int to int. So this is on the right-hand side of an application. So the next thing we need to do is we need to change the type of the function on the left of the application. And so we need to change the input type of this function. And so this function needs to change by this new diff plus int to int to int, which reflects the fact that it's the input changing. And since this expression is a lambda, to change the input type of the lambda, it needs to change the type of that variable in the body of the lambda expression. And then finally, it adds the argument to x. So I've just given one example of how this typed refactoring system works. I won't go into too much more detail in this talk. But in the paper, there's some more math. Basically, we define these diffs form a category. They can be composed and stuff. We have this small step system for propagating the diffs through the program. We prove all the standard kinds of theorems about that, like type preservation and confluence. And just one thing about this that I think is interesting is that the workings of the system are in large part automatically derived from the typing rules of the language. So for example, here's the typing rule for a lambda, and the way that it just knew to change the variable in the lambda is actually derived from this typing rule in the implementation. So that's enough about the math, but back to a little bit of a higher level. I said at the beginning that the goal was to operate on this well-typed typing derivation. So does our system actually always do that? Well, not exactly. So there are some cases where it will need to actually insert an error into the program in order to deal with something. So here's this map function again. And suppose that I want to change the output type of this f parameter. So I'm going to go ahead and change the output type of this from bool to int. And what you can see is that Pantograph has added this, what we call a type error boundary in the program, where there's this discrepancy in the types. It couldn't resolve this by like adding an argument or something. And in a way, this is a lot like what a type checker does, in that it's placing a type error. But it's also different than a type checker in some interesting ways. So first of all, these type error boundaries are actually first-class terms in the program. And what that means is that I can select it with a tree selection. So there I've selected the area inside of the error, but outside of the call to f. And then a second, what I'm going to do is I'm going to delete this type error boundary. Right? Wouldn't that be nice? You have a type error in your program. You just delete the error. But let's think about what's going to happen is that in Pantograph, when you delete a selection, you're telling it that the type inside is the correct type that you want, and it should make the program around that conform to it. So currently, map outputs this type list bool, and when I hit backspace and I delete this selection, it's now changed it to list of int to correspond to that. So let me just show one more example of how this typed refactoring system can place errors but still do something a little bit different than what a type checker does. So here we have this program, this f with 3 integer inputs, and then we have it applied f of 1, 2, 3. And suppose that the programmer wants to delete the second of these 3 arguments. So Pantograph describes this internally with a diff. Again, here it's a minus diff, int to minus int to int to bool. And it's going to respond by placing this other kind of error form around the second argument there. But actually, what you'll notice is that a type checker wouldn't be able to know which of the arguments to place the error on, because all that it would know is that f takes 2 integers now, and it's applied to 3 at the call site. Even if it knew that it used to take 3 integers, that's still right. So the fact that this typed refactoring system actually acts on the edit itself gives it access to more information than what a type checker has. So at the beginning, I said our goal was to make a structure editor where you're directly editing a typing derivation, but yet you can fluidly edit programs. System is not perfect. There's certainly edge cases that don't work so well. But overall, we believe that we've demonstrated that this is possible with these 2 things, tree selection and this automatic typed refactoring system where every edit has a typed meaning. We also ran a user study in which we got 15 or so undergrads. We trained them how to use Pantograph. Some of them learned how to use Pantograph very well. Some of them were completely baffled by it and had no clue what was going on. Overall, the text editor was a little bit faster. But we did, in making this user study, we made a tutorial to teach people Pantograph. So if you go to the paper and you click on this link, it takes you to this tutorial. And it goes through it from the beginning. It explains selections. It has a bunch of different exercises. And it's entirely self-contained. So if you want to try out Pantograph, you can find it in the paper. Thank you.
Thanks. How do you handle comments?
It doesn't have comments implemented, but if I were to implement it, it would probably be a form that wraps an expression and then also has a string where you can type the comment, is probably how I would do it.
Hi, thanks. So in this example you showed earlier when you were reordering these 2 functions, there was a moment when there was no double function,
Yeah.
but the program called double.
Yeah.
And you didn't talk about it, but it turned red. I guess the editor was doing something. Could you say a bit more about what's happening there? And
yeah, so there's
that's a valid program.
Right. So as I said, the goal in general is to try to maintain well-typedness, but there's some situations where it doesn't do that, and there's a few different forms that it puts in the program. So I talked about the type error boundaries in a little more detail. There's this one where it just can have a variable that's been unbound, and then when you repaste the binder, it reattaches it, and then internally it has a De Bruijn index again. So yeah, we would sort of like to unify these different concepts of errors, but they're just different things in Pantograph.
This is really cool. I noticed that most of your all of your examples were simply typed, and I was wondering, have you tried this out on any sort of polymorphic calculus?
What Pantograph does have is it has some built-in functions that are polymorphic. So actually, the example with map, cons is polymorphic, for example, and when we change the type of the list from bool to int, it actually makes use of that. But Pantograph does not have user-defined polymorphic functions. So yeah, that's something still to do. Yeah.
Hi, I had a question about your empirical study. So you said you compared to a normal text editor, and I'm wondering, did you compare to something like Emacs or like a modal text editor or both?
So what text editor we used in the user study?
Yeah.
Yeah, so we made a thing in a browser that used like, I mean, it had like some of the basic features like, red underlined errors and stuff like that. But it was just a custom thing that we made for the user study.
Okay, but did you compare it all to like modal editing in Vim?
Oh, no, we didn't compare it to Vim.
Okay. All right,
Although that would probably require also teaching the participants how to use Vim. But, yeah.
Possibly.
Yeah.
I mean, in my experience with synthesizer generator and all things, like text editors are just, so superior to structured editing, and structured editing just slows you down. But there's Blockly, right? So have you considered sort of drag and drop and sort of, there's a huge amount of use of trees, in these visual languages where kids start to learn about tree structure and programs. So anyway, I think there's an opportunity there. I'm pretty pessimistic, as you can tell, about it for text. And maybe we'll get there. But thank you. Very good. Very, very cool stuff. So there's not really a question.
There's no question. All right.
Right, Neil.
I have a question. Are there modules, or does type changes propagate through other files or something like that?
Yeah, I mean, in Pantograph, it's just a single expression is what's implemented. But
I see.
That would definitely be something to think about.
Hi, this is really nice work. So first I want to say I'm especially excited about this for type systems that are really hard, like dependent types. And second, one thing I didn't quite understand in your presentation is like, do you have like sort of multi-selections? Like, if you have a list of integers and you change the first element to like a string, you might want to like select a whole bunch of things at once.
I'm not quite sure what that means. Yeah, like you have a list of integers, but you change the first one to a string.
Yeah, now it's a type incorrect list. So the change you might want to make might be to apply a function to all the elements in the list.
Okay, so if you had a list with a bunch of integers and you changed that, so that wouldn't be a selection, but yes, you could edit the type of it to turn the first one into a string. What that would do is it would place a type boundary around all of the other elements because they would be expected to be strings now. Yeah.
Hey, thanks for a great talk. The question I had was, sometimes when you make a change, right, and you propagate this through the tree, you seem to have multiple options for what you could do. So in the example that you showed where you added the lambda, right, you could have also just changed the type of the outer thing to be a function instead of like adding the argument to the inner thing. How do you make those decisions? Do you have any sort of model for how to decide this? Or is this just the closest thing in the tree?
I mean, there's a deterministic algorithm, and we've shown it's confluent, so it does a predictable thing. And like, if you learn how to use Pantograph well enough, you definitely can understand what it's going to do. So one side is like, you have to get used to it as the user. But then, yes, there are also situations where it feels like maybe I wanted to do this other thing, and then I have to take some longer sequence to get there. So that could be a problem with this kind of approach, yeah. Absolutely.
Thanks.
So we need to move to the next talk. Maybe you can take the next questions on offline. Let's thank Jakob again.